I'm really excited to be here today with Glen, my friend who is a physicist, because we are going to talk about the Jordan Peterson, Lawrence Krauss conversation, particularly a 2-minute clip at the beginning, well, about halfway through the conversation, I guess, but it's about a 2-minute clip. And welcome, Glen.
Good morning.
And you have some kind of alternate views to those of Lawrence Krauss, and
hopefully complementary. So
okay.
Fill in the missing blanks. Yes.
Fill in the missing blanks. Okay, well, we're going to learn something today about physics. I'm looking forward to that. I'm going to share my screen and just show this clip. And so let's see. I shared far too much of my screen. There we go. Well, now I have the same problem again. I think what happens is that they're kind of changing my default speakers. Zoom keeps changing the rules on me. Well, so I'm going to look at the transcript here and just read the transcript for you guys at that point. It starts at 80.12.
So yeah, I think that's about it.
Okay, so he's just been talking about position and momentum, and Jordan Peterson says, well, it's more like they're concurrent incomprehensible descriptions rather than explanations. And Lawrence Krauss says, well, yeah, well, you accept the theory. That's what you can predict, obviously, and it works. But I mean, there's something you've hit on, which is really important. A lot of people get hung up on the interpretation of quantum mechanics, and people write books about it in many worlds. And they, lately there's somebody who wrote a book and tried to sell books. But the point is that it's nice to talk about all that, but it's really irrelevant because that's actually a brilliant, I first realized it due to a colleague of mine at Harvard who was really the smartest person there in the physics department. He's now dead. Lawrence Krauss talks in a really funny way, doesn't he?
Yeah.
He just goes on and on. Sidney Coleman. He said the proper thing to talk about is not the interpretation of quantum mechanics, it's the interpretation of classical mechanics, because the real world is quantum mechanical, and any classical picture we impose on it is going to be crazy. But you don't have to think of it as real. They're all just different approximations to a reality, an underlying reality which can't be described by any classical picture. So that's why all these classical pictures seem crazy, because none of them is complete. Well, if you look at it, I guess so now it's going to be Jordan Peterson. Should I go on with Jordan or stop?
We end where Lawrence Krauss uses the word illusion. And that was the big red flag for me.
Okay, so Jordan Peterson goes on to say, well, if you look at this psychologically, I'm going to refer to Piaget again. I mean, Piaget pointed out that we derive our concepts from our practical manipulations of things. So for example, you might ask why. Well, why is this one thing? I could say, well, it's 5 things. Yeah, well, the question is, what's a thing? Well, look, it moves as a unit, therefore it's a thing. So that's 1. Well, it could be 5 if I broke it apart. Now it's 2. But it's like the concept itself is predicated on our interactions at this scale. And so we're going to derive our sense of reality from our practical interactions at this scale. And your claim, the claim of the quantum mechanics in general, is that it doesn't apply at the micro scale. So our intuitions are gone because our intuitions are predicated on our embodiment at this level of analysis. And at that point, Lawrence Krauss jumps in and says, absolutely. In fact, the purpose of the greatest story told so far, that particular book, is to say something remarkable. The world of our experience is an illusion. I know I hate to say it because it breeds all sorts of mumbo jumbo and people start doing it, but at a fundamental scale, at the small scales, everything that defines our universe, including matter and mass, really the things that make the universe we experience are really accidents of our circumstances rather than fundamental properties of the universe.
I think we can stop there.
Okay.
So like I said, the first red flag was when Lawrence Krauss used the word illusion. And that's not a word that belongs in a physics discussion. So I need to, that 2 minutes has got a whole lot of things which just don't make sense. And I'm sort of slightly, well, I haven't been impressed with Lawrence Krauss for a long time. And so I thought I could come in and at least bring the physics and get the physics correct for your audience and
Okay.
and help make sense out of it. And so I thought I could focus on that little transition there where he talks about classical and quantum approximations. And if we can expand on that, maybe, and then come back once I've gone through the whole quantum mechanics, classical mechanics, contradiction apparent, then we can sort of branch out and explore some of the other stuff that was brought up there. So Jordan Peterson's, his background in physics is weak, but his intuition is really good. And I get disappointed with Lawrence Krauss because he doesn't pick up on that. There's a lot of things that he could have helped Jordan Peterson with. So we'll take that. We'll start down that path. And the big conundrum that comes up is the distinction between classical mechanics and the world of quantum mechanics. And they make a lot of deals of that. And then Lawrence Krauss gets to the point where he's saying, well, the classic interpretation is just the approximations. We'll never know true reality, which is the quantum world. And then I think he launches on that to use the word illusion. And I totally disagree with that. In fact, I'm surprised that Lawrence Krauss would even make that statement. And we'll come up to that in the next few minutes. So the distinction between classical mechanics and quantum mechanics, and the big mystery that seems to inspire a lot of speculation and metaphysics. And it's never really been brought, I think, fully dealt with in the public sphere. So that's what we're going to do. When I first started talking to you, I was really hesitant to get too technical because I was afraid I would leave your viewing audience behind. But I've come to realize that the people who visit your site are actually far more sophisticated than I had originally thought. And so my worries are going away. So we're going to take the red pill and we're going to go all the way to the bottom of the rabbit hole right now. And you're going to see things that you haven't probably encountered. But I'm going to take you to the bleeding edge of where physics is. And then once we're there, you can make of it what you want. And then we'll come back and start looking at the further elements of the conversation. So generally, you've heard the term quantum mechanics and classical mechanics, and just for ease of speak, I'm going to say quantum versus classic worlds. And okay, the best analogy I can think of to start this conversation is the classical world is like an oyster and the quantum world is like a pearl. But inside the pearl is a grain of sand that irritated the oyster, and the oyster started producing this beautiful shell around the grain of sand. But somewhere inside that pearl, there's initially a grain of sand, that something that irritated, didn't fit, didn't work. So quantum theory has grown up out of classical mechanics in its attempt to explain something. It's become really great. You know, as Lawrence Krauss points out, there's areas in quantum mechanics where you can theoretically predict as many decimal places answers as you can experimentally verify. But down deep inside, there was an initial contradiction which has driven everything else. And so that's where I want to take everybody to. And the other part in the world is that there's no clear, satisfactory definition of what classical physics is versus what quantum mechanics is. We use the terms a lot. Everyone seems like they understand it, but there is no good, solid definition. And my hope is if we could get down to that grain of sand, that contradiction that separates the two, then it'll help us understand a better way to describe these two different worlds. So starting in about the 1930s, they realized that there were some problems with quantum mechanics. You know, the wave-particle duality. If you set up an experiment to look for a wave, you'll see a wave. If you set up an experiment to see a particle, you'll see a particle. But then there was this little funny thing called entanglement. If you take two particles that are entangled and they go different directions, and you have two different observers making experiments, then if one observer makes an experiment to look for some aspect, does that mean that the other observer now has to see the same thing, or can the other observer see something different? And it took its first form as the EPR paradox, Einstein, Podolsky, Rosen. And it's been there all along. They've come up with a lot of explanations for it, attempts to get around it. And along the way, it became accepted, or at least speculated, that the quantum world had its own set of rules. And we in the classical world simply didn't have access to them. So that's one of the things that Lawrence Krauss is alluding to, that the classical world never is only an approximation of the quantum world. Well, those theories kind of come under the heading of hidden variable theories. And people have been exploring that stuff experimentally and theoretically since probably, I guess, the 30s. Somewhere, I think it was in the 60s, the physicist John Bell proposed a very clever experiment. It was a thought experiment at the time that would hopefully decide once and for all if there were hidden variables or not. Is the quantum world acting on its own set of rules that we don't know about? Or is everything we see what the quantum world has? And so he proposed this experiment, and if the outcome was a certain value, then hidden variables were allowed. If the outcome was different, then hidden variables would be excluded. Well, in the 1980s, they were finally able to get the technology to do this experiment involving entanglement. And lo and behold, John Bell's inequality, I guess, was proven. There are no hidden variables. So Lawrence Krauss is wrong in that sense, that the classical world has access to everything that the quantum world has. There is no hidden variables. There's no mysterious forces acting in the quantum realm that we don't have access to. So I think it's like a magic trick. You keep watching the magic trick over and over again, and you know it's a trick. And so you keep looking for the trick, and you never see it. And then one day, you know, Bell's inequality is proven, and you realize there is no trick. So they often say the world of quantum mechanics is strange, stranger than you can think. Well, it gets weird, and it keeps getting weirder. So we'll start with entanglement, was what came out of John Bell's inequality. And that started the whole quantum computer stuff, everything dealing with entanglement. A whole raft of experiments have come since then, and they've all come back to the same conclusions. So I thought, what is quantum mechanics versus what is classical? And so I thought we'd start taking this apart. first, I think most people think of quantum mechanics as the physics of the tiny, the small, and classical is the physics of the big, extended, composite. Well, that's not correct. If you go into the quantum realm, we think of single particles as being quantum mechanical. That was one of the first things that cemented the notion of wave particle duality. Was an experiment that showed that electrons, which they knew were particles, actually displayed the double slit diffraction pattern in an experiment too. So, but since then, they've kept doing that, and they've got molecules now of over 100 atoms have been shown to demonstrate quantum interference in a double slit type of an experiment. So the whole composite objects, like Jordan Peterson was holding up something, I'm not sure what it was.
I think they were these kind of toothpicks that you can.
I was wondering about that.
Yeah, yeah.
So yeah, Jordan he's getting on it. Composite objects, I mean, at least atomically really big, can still act quantum mechanically, even though they're extended and made out of many atoms. My thesis work was defect centers in a crystal lattice. In this case, it was ammonia ions, NH4. These are 5 atoms, and floating around in a crystal lattice, and they behaved totally quantum mechanically, tunneling around. So here's a 5-atom molecule still behaving quantum mechanically, even though you would expect something that size to act more classically. And we've even gotten to the place, and this is a place on paper I'm trying to get through right now. They've shown quantum entanglement between 2 mechanical oscillators. So these are basically acoustic, drumhead oscillators. They're just a metal film that are oscillating up and down, described totally classically, but yet they're demonstrating quantum entanglement between those objects. So people's intuition of quantum it's not about size. Extended objects can still behave quantum mechanically. And then there's a whole other area of things that aren't really particles, but still behave quantum mechanically, and they're called quasi-particles. And I think that was one of the references I'll include. There's at least 3 or 4 dozen of these things. They're like chimeras. I guess that's the only way I can think of describing them. Under certain conditions, if you tune everything up just right, you'll get these hybrid behaviors in a condensed matter solid situation that they're not a particle, but yet somehow this phenomena that has come into expression behaves exactly like a particle. So, there again, the question is quantum mechanics dealing with particles? Well, no, there's things that aren't even particles that sort of take on this composite behavior that acts like a particle. So that's not a good distinction between quantum and classical. So it's getting down to the real area, the real distinction between the quantum and classical is this notion of entanglement. And that's where I've come to over the years. That seems to be the place where it all starts. And so I'm going to talk about entanglement and what that implies. And I think I gave you a short video on, it's a great classical physics example of what entanglement is. And so it runs about a minute, and it's worth watching because the phenomena takes about a minute to actually happen. So.
Okay, I'm going to pause us for a second here while I get the sound working on that video. Okay, so we're going to share screen and look at this really fun video. And for some reason, the sound isn't working on it, but I think we don't need the sound. It's pretty much a visual anyway. So what's happening here, Glenn?
So they're setting 5 metronomes off in random order. Now it takes about a minute, but if you watch, they'll all start running in lockstep.
Now, it seems to have something to do with the fact that it's sitting on these 2 Coke cans.
Yeah, they're coupled together through the motion of the board or the styrofoam sheet it looks like they're sitting on. Yeah, so
I noticed this one over on the left, it took a lot longer to kind of
Took a
line
lot
up with the
longer.
rest of them.
So those of your viewers should click on this in the reference, because it's much nicer to get the sound. And I noticed the video is a bit choppy here as well.
Yeah.
Yeah, it's much smoother in reality. So I guess we're talking up to
Okay, now the
technical
sound
difficulties.
comes on.
What?
Yeah, so everybody should certainly check out the link in the description below so they can hear it with the sound on. The sound's not working right on my computer today, but in the future.
Okay, so I thought that was a great example of classical entanglement. We have 4 mechanical oscillators, the metronomes. I wonder if any of the younger generation even knows what one of those is. And as you watch, they all start out randomly, but because they're coupled very slightly together through that plate or board and on the cans, it allows the whole thing to move back and forth. They eventually synchronize. And so this is a classical example of what you might call entanglement at the quantum mechanical level, when you get multiple states, oscillators or quantum states, all lined up and they create their own little wave function together now. Now in a classical realm, if we took our metronomes and we got them all synchronized, and then very quickly and very gently we moved the metronomes from the kitchen table out to each in a separate room, each metronome would now be exposed to a different environment, heat, wind, breeze, or whatever. And so you'd expect very shortly the metronomes would all get out of sync again and they'd be all randomized.
Mm-hmm.
In the quantum mechanic world, you would call that decoherence, that the entanglement's breaking up and then it loses sync and everyone goes their own way. Now imagine the metronome experiment. You've got them all synced up. You quickly, gently move them all into different rooms. And while they're still going in sync, you bump one. And all of a sudden you notice the ones in the other room glitch. And if you saw that happen in real life, you would think you lived in a haunted house. But essentially that's what happens at the quantum mechanical world at that level. We don't, bumping the metronome is a classical example, but in the quantum world, we talk about making an observation or making a measurement, which then, as I say, collapses the wave function down to whatever the experiment is looking at. If you start out with entangled pairs and what you do to one of the pairs measurement will affect what a second observer a far distance away will see. And that is the big head scratcher.
Okay, will I throw you off if I ask a question?
No, go please.
Okay. I often hear physicists saying that there's no human observer necessary, that the observation can just be made by a machine. And
Yes.
That seems so strange to me because a human observer had to make the machine or design the machine. So isn't it still a human observer doing the observing?
We'll get to that.
Okay.
Yeah,
Okay.
the conversation will get there. Yeah, but
Okay.
it's a good question. It needs to be answered. So John Bell's original thought experiment dealt with 2 observers, and they're since been known as Alice and Bob, Lab A and Lab B. And so you'll always see Alice and Bob now mentioned in quantum mechanics as 2 different observers that are separated in a they say space-like separation, which means there's no signal. They're so far apart that there's no signal can get from one to the other at the speed of light. So when Alice makes her measurement, it immediately affects what Bob is going to see. And so how do you deal with that? This quantum weirdness. So we'll just leave it at that. And we'll move on to the next weirder example. And this is the PBS video. It's called a delayed choice quantum eraser. And it was a double slit experiment. And if you watch, well, the double slit experiment, hopefully people know what this is.
Mm-hmm.
The particles go through a particle, something goes through two slits and leaves a diffraction pattern on a screen. Now, if you try and look at which slit the particle went through, you'll destroy the diffraction pattern on the screen, and you'll just see two lines where the two slits, a ballistic trajectory, would have taken things. So they've been trying to clever, so they've come up with experiments that don't look at which slit you went through until after the particle has hit the screen. So that's called delayed choice. Mm-hmm. So you let the particles come through, you let them make a pattern on the screen, and then you measure later which slit they went through. And lo and behold, if you measure the slits later, the pattern goes away. But you think, wait a second, the pattern's already there. How can measuring something later affect something that happened earlier? And this is the puzzle that entanglement spawns, is this apparent fact that the future can affect the past. So and so that's the crux. If you're looking at where the quantum world disconnects from the classical world, it's that apparent behavior that somehow the future is affecting the past. It's either that or there's something weird. And so you keep coming up with theories to explain the weirdness, but this notion about the time, future to past, it's like a stalking horse. It follows every experiment around, and it's always there. But I've noticed a lot of the popular science presentations, even like the PBS one, don't really tell you that that's an option out. So we're going to keep going with this. So I would really like everyone, if they're interested, to watch that YouTube video, because I think it's the best explanation and layout of the experiment itself that I've come across. And I think it's pretty straightforward.
Yeah, I'll link to it.
It's too much.
I had tried to read an article about that delayed choice experiment, and it just went over my head. But when I watched the video, it made complete sense. So,
right. Yeah. So his explanation, his layout of the experiment is correct, and he does a really good job. But he doesn't dot the I's and cross the T's at the very end, and which is why I've included the actual paper in the reference that you're going to post under the film.
Okay.
I mean, under this video. It's a physics paper. It's only 4 pages long, so it's tiny by physics standards, but there's something in there that is different than what he says in the video. And that what is missing in the video is the thing that's most important. And if you look at the actual paper, and
would you like me to share screen on the paper?
If you want, people can look at the title. But it's turned into a classic experiment that has spawned a lot of copycats, and people have done it better.
It was the archive one, this delayed choice quantum eraser. Okay. Mm-hmm. And do you recall where it is in the paper? No,
I'll explain. It's something you have to read through.
Okay.
there's a subtlety to how the experiment is done, which is left out of the PBS. If you listen to the PBS video, they'll talk about observers, and somehow the observer affects the patterns that you see. But in the experiment, there is no human observer. And this is beginning of the answer to your earlier question. The first time an observer looks at the data is when they open up the files on the hard drives. This experiment just turned on, they let it run. It's completely passive. It doesn't interact with the photons at all. Just a quick, if you can look at the picture there, they do the delayed choice by taking a photon, creating an entangled pair, twin to it. One of the twins goes through the double slit and makes the diffraction pattern. The other twin is the one that wanders off for a while, and then later they measure it. And
So
since they're
are we
entangled,
looking at the bottom picture or the top picture?
the one that you got your arrow on, your cursor on right now,
Okay.
that's the nature of the experiment, and it shows the detectors. So that's one of the arguments in physics, is what constitutes a measurement or an observation. The detectors, the electronic signal, the pickups, that's the observation. That's when the quantum mechanical object, in this case the photon, becomes a classical object, which is a pulse, electrical pulse in a wire. So there's an interface. That's when the transition happens. No one's really talked about it in physics. It's still a wide open area, which is just a footnote that I keep wanting to bring up. Is that so much of the physics that's presented in popular presentations never takes you all the way to the cutting edge. They always stop short. So the real mystery is still waiting out there, but I think it gives people the wrong impression that a lot of physicists really know stuff that is still open for debate.
So let me just clarify. The thing that's still open for debate here is that the entangled particle is actually becoming part of an electronic circuit.
Well, at some point, that's the observer. You ask about the observer being a human, but it doesn't have to be a human. It can be silicone, particle detector, or it could be a photomultiplier tube. Anything that makes the transition from the quantum world to the classical world, that's when the observation happens.
Well, sure, but all I'm saying is that whatever that system is that's observing it, that system was created by a human.
Yeah. Mm-hmm.
So there has to, there's a human element to it, whether the human
For the
is
sake of it,
there or not.
Mm-hmm. But in nature, even if we weren't here, Mother Nature is still doing this. It's still making the transitions from the quantum to the classical world. Happens whether we humans are here to watch it or not.
Well,
so,
see, that's the thing I never hear anybody talk about. We know that the quantum world lies under the atomic world, but nobody ever talks about how quanta turn into atoms and how atoms turn into, to some extent we understand atoms turning into molecules and all that, but how did the quanta get into any of this stuff? That's the part that nobody ever talks about.
So we're heading there. That's
good.
That's the end of the rabbit trail, or rabbit hole. So in the experiment, I must have read through this paper dozens of times, looking at it. Like I say, it's a magic trick. Where's the magic trick? And then it finally hits you one day. There is no magic trick. The photon comes through. The detectors measure whatever the photon decides it's going to do, and that data is collected. And if the photon decides to let you know which slit it went through, then you won't see the diffraction pattern. If the photon decides to hide from you which slit it went through, then you will see the diffraction pattern. There is no observer making a choice that affects experiment. the output of this experiment is entirely what the photon has decided to do already. Okay, now.
So wait,
stop.
photons have free will?
Maybe, which gets
Wow.
us to the next step. It's like the Matt O'Grady or O'Dowd, who's the narrator of the PBS series. He's an astrophysicist in his own right, but
Mhm.
he makes this great comment, and I like it. He says, "Can it get any weirder? This is quantum mechanics." So yeah. But generally, where the PBS video stops is where your exposure to the problem stops. But the problem keeps going. And so we've taken the red pill, let's keep going. We can close this out. And the next video that I really would like people to watch is, do electrons have free will? It's the Conway-Quotient free will theorem. It came out in about 2007, I think. My memory, actually quite recently. There was a whole series of YouTube videos that I think the narrator, I think her name was Dolores. She did 5, 6, 7 years ago, that really dove into a lot of these very esoteric questions at the cutting edge of physics. And this is one where she took on the free will theorems. And this is a very neglected theorem, but very important, probably the most important one I can pass on. So I would really suggest that you watch this video for sure and check out some of her other ones. So,
okay, so everybody needs to stop the video at this point. Go on and watch that. I'm gonna.
or just listen to me and then go back if the spirit moves you
Okay.
to dive deeper.
Okay, I'm gonna put a link to it below. So
just be forewarned though that her health has taken a dive in the last year or so, and so
I'm sorry to hear that.
her latest video post is not happy.
Oh,
But
well,
the other stuff is
that one
great.
that you're recommending, and it's excellent. It's really, really good. Yeah.
So it was when wrestling with this delayed choice quantum eraser experiment that the free will theorem and why John Conway, the mathematician, chose the name free will finally sunk in and made sense. So the free will theorem is a thought experiment in mathematical physics, the same as John Bell's original proposal was. But it takes Bell's work and incorporates special relativity into it. Now, if you remember your special relativity class, anyway, if two events are space-like separated, which means they're farther apart than a light signal can go between the two of them. So there's no way that their history can affect their history. Now, in relativity says that you can pick an inertial frame in which event A, Alice making her measurement, happens before Bob making his measurement. But I can also pick another inertial frame in which Bob makes his measurement first and Alice makes hers second. And so they came up with a clever experiment, just like John Bell did, for a relativistic invariant quantum mechanical measurement that they could let Alice and Bob do. And then showed that the result is invariant which frame you're in. So the order that Alice and Bob make their choices to make their observations don't matter in the outcome of the experiment. So if you just looked at the original Bell's experiment, you would say, well, Alice made her measurement first, and so the entanglement pair made Bob's measurement happen. But now what the free will theorem says, it doesn't matter. The outcome is independent of who makes their measurement first. So that means the electron must have decided what it was going to do before anybody made any measurements, because there's no way, or unless the future can affect the past. So that's one of the axioms in the free will theorem, is what they call locality. In other words, the effects can only happen in to events that are local, that can sense each other. But once you get far apart, an event out here can't affect something over here. But in the quantum mechanical world, that does happen. So it appears that either the electron has some choice, free choice, as what it wants to do, and then just shows you what it's going to do, which is the quantum eraser experiment with photons. That is the most clean explanation, is that the photon already decided what it's going to do, and then just showed you, the observer, what it decided already. Or non-locality is a factor. In other words, the future can affect the past.
So
So
when they
there's-
talk about non-locality, that's what they mean? This,
Right. So
quantum
it is, you know, in the relativity sense, space and time are the same, treated as the same thing. So saying that the past or the future can affect the past is saying the same thing as two objects that are farther apart than the speed of light allows a signal to travel can still affect each other. It's kind of mathematically saying the same thing. But that's one of the reasons I want people to look at Dolores's video on Do Electrons Have Free Will, because she talks about what is in physics is called a free choice. Now, the term free will is very loaded and carries a lot of baggage. But in physics, the term is much more defined. It's called a free choice. And that is a choice which is not dependent on any past event in the universe. So if you assume that Alice and Bob have free choice to decide what kind of experiment to do, you know, then the electron must have had free choice in deciding what it was going to show them, what it was going to do ahead of time, providing locality is sacred. So I've gotten in trouble in the past for using the word choice, but this is one of the reasons I use it, because in physics it has a much more definite meaning. So now that we're bumping the bottom of the rabbit hole now, it seems as if the quantum world can be best explained if there is no past or future, no here or there. You don't say the past affects, the future affects the past. You just say there is no time in the quantum world. And I know people don't like it, but you can't say it's wrong. That's one of the, like I say, I call it the stalking horse in all these experiments. The possibility that what distinguishes the quantum world from the classical world is in the quantum world, space and time, distance have no meaning. Everything is instantaneous. Whereas the classical world is a world where time and space do mean something.
so when you say that there's no time in the quantum world, would that also mean then there's no space?
Yeah, everything to the photon in the delayed choice experiment, everything was instantaneous.
Well, is this like that thought bubble that one physicist came up with one time? I can't remember who it was. Maybe it was one of Feynman's mentors, that there really is only one particle.
Yeah, that was it keeps going backwards and forwards in time.
Yes. And that at any moment in time you take a slice, and then the slice is all the particles that appear to be there, but really it's just a slice of this thing going back and forth.
Yeah, I remember that, but I don't think it ever read anywhere.
No, it didn't. But if you think about there being no time and no space, it sounds theoretically possible then that could be what we're actually looking at.
But that's one of the unexplored areas which I find fascinating is retrocausality. I mean, there are physics papers and there are researchers who actually are taking that possibility seriously, that the future affects the past, and looking at it theoretically and running the math. And so
Well,
it's
I mean,
out there.
we certainly see it in psychology. We certainly see it in the way that our minds work, in the way that our stories work. We see that all the time, that things that happen in the future can rewrite the things that have happened in the past in our lives. And that the TikTok thing, and so the TikTok thing is totally what happens when you put a number of women living together in the same house, because their cycles all line up within a month. They all have the same cycle. So that, I mean, that's some kind of classical entanglement that's very
Right.
strange, the way the human body works. So,
So this is we've hit the crux. You know, this is the grain of sand that creates the pearl of quantum mechanics. This contradiction or paradox or mystery that somehow the quantum mechanical world can best be described as a world where time and space don't matter. As soon as you try and put our notions of space and time onto the quantum world, that's when all the contradictions and the weirdness shows up. And I don't expect this to make a lot of sense. It's just something I've been wrestling with for years. And when you live with something, after a while, it starts to, wait a second, you know, you start seeing patterns. And this seems to be the pattern that keeps coming back to me when I look at all of these papers. Now, again, quantum mechanics is a set of rules. It's not a set of objects. The classic, the mechanical oscillators, I included a link to an article on that. I think it's in Physics Today, just this recently. It's called An Example of Quantum Entangled Mechanical Oscillators. So these mechanical oscillators, they're like 10 microns on a side. And I think human hair from very fine to thick is like 20 microns to 150 microns. So these are mechanical drumhead oscillators, smaller than the diameter of human hair, but still composed of probably 1 million atoms or more. So these are huge, extensive objects, completely governed by classical mechanics, but yet are still displaying quantum entanglement. So that's what I'm trying to get. Quantum mechanics applies to a lot of things, extends beyond what people normally think. So the way I look at it, getting back to Lawrence Krauss, we're not two different worlds. There's not the classical world and the quantum world. And the quantum world is the real one, and the classical world is forever an approximation. It's best to look at one universe with two sets of rules that intertwine. A board game with pieces and two sets of game rules playing at the same time. So we see everything the quantum world does. There is no distinction. There's no hidden variables. There's no mystery. Our world is not an illusion. It is what it is. It is what it's supposed to be. And a funny thought came when I was listening to Lawrence Krauss, was that for him to talk about the real world being an illusion, I thought it would be like going to church and hearing my pastor give a sermon that God isn't real, but he's a useful approximation nonetheless. So I don't think Lawrence Krauss takes physics. To him, it's not sacred. That's the word that comes up. He is a professional atheist, so that would be expected. That's why I always like Nima Harkani Hamed, put a plug in for his stuff. I think he does take physics in a sacred sense. It's not a joke. It's not an illusion. He sees that there's a capital T truth out there, and it is maybe not fully knowable, but accessible, approachable. Lawrence Krauss rejects that. To him, the real world is forever and always separate from us and unknowable. I don't know if people pick that up in his words, but as a physicist, that's what I got out of them. That
Well, also when he said that our universe and everything in it is an accident of circumstances. What does that even mean?
Yeah, a lot of things he says don't make sense to me if you stop trying to.
Well, and Jordan Peterson tried to pull him back and say, well, let's look at the very beginning when these very orderly things began to happen and the chemical table started to develop,
Mhm.
But he just kind of blew right past that. It's just all an accident and circumstances. I could tell Jordan Peterson is on some kind of a trail, and it seems like he's on a trail very similar to the kind of trail that I've been on, which, I mean, I'm not trying to say that I'm as smart as Jordan Peterson, but the questions that have occurred to me over the last 20 or 25 years are very similar to the questions that occur to him. Like this whole idea of not being able to get down to the energy, not being able to get down to zero when the was it an electron that's in the bottom of
Yeah, there's no zero energy, because then you'll know the momentum is zero, in which case you're in the quantum world. There's certain variables which are conjugate. You can only measure one. As soon as you measure one perfectly, then you lose all information about the other.
So if it's in the bottom of a potential well, it's always going to be more than zero.
Mm-hmm.
It's always going to be up a little bit above the bottom of the potential well. And you can see Jordan Peterson zoning in on that. There's something in his mind that you mean it doesn't go to zero? For some reason, something going to zero is very meaningful for him. But I think he probably realized it wouldn't do him any good to pursue that question with Lawrence Krauss, because Lawrence Krauss wasn't going to be able to give him an answer to what he was really looking for.
So,
do you have any idea what he was really looking for when he asked that question?
No, but I keep getting the sense that, like I say, Jordan Peterson's intuition is, I think, very good. His questions are telling me that he's on to something. Like, I guess you've picked up on that same thing, but he's having a hard time articulating it. I think he picked Lawrence Krauss to talk to in the hopes that Lawrence would help him. I don't think Lawrence Krauss was a good choice.
Who would be a good choice for him to talk to about these things?
No, because Jordan Peterson, I've used the word, he's captured by the transcendent. Jordan Peterson is in touch. He's plugged into something that most people aren't, which is what's driving him. And I think that's why the idea, intellectual dark web, has sputtered out, is because Jordan Peterson is still plugged in and he's still trying to figure it out, but no one else has been able to plug in where he has. And so I think that's why the momentum has run out of it.
Well, so do you think Nima Arkani Hamed would be able to answer some of this questions?
I have no idea. Nima is he's like in his own planet. But Nima, of all of the physicists, is not afraid to take on, they call it the dreaded A word, the anthropic principle. Even though he professes to be an atheist, he takes the concept of capital T truth as a sacred obligation in physics. And he's not afraid to tackle the anthropic principle, or not to run away from it. So in that sense, spiritually, he might be a good person for Jordan Peterson to talk to, but I'm not sure beyond that if they'd have any commonality.
So what is the anthropic principle?
It's this observation that everything in this universe seems to be perfectly dialed in for us to exist.
Oh, so like the constants and all that.
The constants, the size of the age of the sun, the age of the universe, the Earth's orbit is just right. The fact we have a moon, you just go down the list, and there's everything. It seems to be dialed in almost exclusively for us, or for something like us to exist.
So that's why there's only really two choices. Either we exist here for a reason or the multiverse.
Or the multiverse. Yeah, that's the only physical reason for the multiverse, is they need to just say, well, it was all random. Well, if it's all random, then there has to be, countless infinite number of random choices out there that we would actually happen.
So what you're saying, I think, is that there are many physicists who don't take the anthropic principle seriously. So they don't see only those two options. They see some other options.
Yeah, they're forced into other options. I was challenged once with a very good question. I was asked, how do you know as a Christian you're not seeing things in physics, that you're seeing things that aren't there? And that's a good, solid question. But the only real good answer is, well, how can you as an atheist not know that you are not seeing things that are there? Are you letting your atheism block you to accepting things that may be true? And I think Lawrence Krauss, if we were to keep going on his interaction with Jordan Peterson, it keeps coming up. I keep sensing it, that there are places Lawrence Krauss will not go, options he does not consider, because that might bring up the possibility of some kind of transcendent thing going on, some reason. It doesn't have to be a spiritual. The whole question of why does complexity grow? I notice he dodged that completely. It's all a mystery. It's all random. Again, like I'm saying, well, gee, why are you doing physics then?
Well, so one of the things that occurred to me in this idea of what is out there to find is, for example, with mathematics, I watch that Closer to Truth guy quite often, and he has many, many videos where he's asked different people, is math invented or discovered? And people have different opinions about this. Some people say it's invented, some people say it's discovered, and they seem to have good reasons, both of them, for what their opinion is. But when I stop and think about it, like this morning, I was watching a video on somebody's conjecture. I can't remember the name of the guy, but he had a conjecture. Are there going to be a certain number of other places where this thing shows up? Often these conjectures are, will we find an infinite number of primes if we continue with this particular list, or will we not? And those kinds of questions. If you ask that kind of question, you're automatically implying that there's some sort of mathematical space that can be navigated that nobody's ever been to before.
Yeah.
If so, then there has to be something that's not invented by humans.
Yep. Totally.
What am I missing?
You're not missing anything. So, but now I'm here on the atheism in physics. It goes way deeper than that. And again, I'll take your listeners to a place that I don't think they've gotten to. If you look at people like Lawrence Krauss, who reject the spiritual and religious, okay, that's fine. That's a reasonable, rational approach to life. But if you ask them about things like strong emergence, they will be dead set against strong emergence. If you ask them, is math invented or discovered, they will reject the fact that it's discovered. There's a pattern there of which the atheism is just a part of. So there's something deeper psychologically going on in people's minds that makes them reject any possibility that there's something else out there. So that would be something to explore. That what is really going on with this? Because, like I say, the atheism is not their main pattern. There's some deeper pattern in rejecting anything that suggests that there's something to the universe bigger than us. So is math invented or discovered? Well, I'm firmly in the camp that it's discovered, that that we find out this stuff and it controls us and it inspires us. And that, in a sense, is pulling us forward into complexity. The fact there's things like that out there to be discovered. Whereas if you say that math is invented, that means we're pushing it from below. There's nothing out there pulling us. So then it's hard to justify how the complexity grows in the world, in the universe, if you have to push it from below, because that's not what the laws of physics tell you is going to happen. I think I've just lost everybody now.
Oh, no. I mean, that totally makes sense. Well, while you're talking, the picture I get in my mind is trying to push a string, right?
Exactly.
Yeah.
Oh, that's I've been saving that one. I'm not sure. I put myself through college. One of my main jobs was working as a rigging man with cables. That was one of the jokes was, if you think pulling cable out by hand is hard, you should try pushing it. And that's the image I often see, if you're a materialist, a physicalist, if you just look at the laws of physics that you can measure and see, if you try to find ways that drives complexity, drives intelligence, drives evolution, then that's a hard way to go. It's much easier to imagine that there's something out in the universe pulling us or leading us forward.
Mm-hmm.
Complexity wants to grow because there's something out there that it's trying to get to. And it doesn't have to be a God, but people like Lawrence, they don't even accept the fact that there might be something in the universe pulling us. So, it could still be a perfectly physical explanation, but they don't even like that. So that's a talk for another day to explore.
Yeah, well, what I would like to do, if we have time to do it again in the future, is tackle that second section that you were talking about on their video. And between now and then, I'm going to solve the sound problem with my share screen, because I just had to update my operating system. And so something must have happened between Zoom and my operating system that needs to be updated. Zoom is often a little bit behind on some of these updates.
Okay.
So it might be a few days before I can get that worked out. But once I get it worked out, then we can actually share screen and show some of the video, and then we can stop it intermittently and talk about it, which I think would be really great, because there's a lot to be plumbed here, and I'm pretty excited.
Well, actually, there's one more layer yet to that grain of sand, which is one of the things that keeps dragging me forward. That if you imagine that, okay, just I'm off on my own world. You can take what I said with a grain of salt or however you want. That what distinguishes quantum from classical is that in the quantum realm, time and space don't matter. Everything is instantaneous. The classical world is where in a place where the time and space have meanings. Things are locally confined. And you notice that if you believe things are, the classical world values of locality are valid, then you have to give the quantum world free choice. If you don't like the quantum world having free choice, like we do, then you have to take away the locality. But notice that the free choice goes away with the locality. They're balanced. They're somehow tied together. Now, if you think about information, how do you make choices? How do you, computation, that's one of my big things, which I think might be a bad word, maybe just conditional choice making. If you wanted to make choices, you can't have the future affect the past if you want to have a world where choice and information make sense. So you can't have a creative process, which is building up from smaller to bigger to order. You can't have order in a world without free choice. So time and space being strict is what you need before you can have creativity and choice. And so that's one of the things that really sparks my interest when I see that happens. A world the quantum world can't support computation, despite all of this the talk about quantum computers. You can't compute with quantum mechanics. You need a classic system that has memory, stability, locality, the ability to go chunk, 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 before you can have intelligence, choice, memory, information, all of that comes out of that. So that's one of the things I'm noticing about the distinction between classical and quantum is, anyway.
Would it be fair to say that one of the differences between classical and quantum is boundaries?
Yeah, you can't, in a world like the quantum world doesn't have boundaries in the sense that we know it. You have to have locality in order to talk about choices, There has to be a before and after. There has to be a separation. There has to be something that fixes a choice once it's made. If you don't live in that world, then none of that makes sense. So if I was God and I was making a universe where intelligent, creative entities like us could come into being, I would have to create a world governed by classical physics laws. So that is as real, I beg to differ with Lawrence Krauss. The classic world is just as real as anything. It's the world we live in. It's not a mystery. There's nothing hidden. So,
okay, now if I were a genius, I would take what you said during this video and I would collapse it down into like one really succinct paragraph, capped off by what you just said, and I would find a way to get it to Jordan Peterson, and I would say, you're on the right trail, just keep going.
Yeah, well, that would be nice, but I'm sure he gets like dozens, if not hundreds of free advice emails every week, so.
Yes, but remember, I did talk to his wife once, so maybe but I would have to find a way to put it together in a way that actually answer some of his questions, so that he would, because I think, well, how I've been hung up on this issue of boundaries for a long time, and I had an intuition that there's something there at every level that goes all the way through, and now you just tell me that the quantum world is in many ways without boundaries, without spatial boundaries, and without temporal boundaries.
Well, you could say that, and you can't argue theoretically that that's not true. So that's an option to put in your toolbox the next time you think about quantum mechanics and how people are talking about it. That's one of the options that's not on the table, but it is there theoretically.
Wow, very cool. Well, okay, so let's next time we talk, let's take a look at that section that's at like 1 hour and 40 minutes and something.
Yeah, there's that is huge. I think that's quintessential Jordan Peterson at that point. So
sounds good. Really good
okay.
talking to you, Glenn. Have a great week.
Take care. Bye.
Bye.